That's intro. Alright, so today we're going to be talking about the integrals and more physics stuff.
No,
More physics stuff.
Wait, are we saying things?
Yeah,
Oh, I love Salish on Instagram.
Is that a thing?
Yeah.
Oh my gosh. I don't even want to know.
I know, those guys must be such terrible people.
Oh man. Okay, let's do the second derivative test. Okay, so if your second derivative, let's go over before we do second derivative test, what second derivative tells you. So if the second derivative is positive, what is the original function doing? Concave up, nice. And the first derivative is increasing, good. And if the second derivative is negative, the original is concave down, nice. And the first derivative is decreasing. And if the second derivative is neither, then the original function possible. Point of inflection, right? And then the first derivative has a possible max or min, right? If the second derivative is neither. But it's only possible if the first derivative, or if the second derivative goes from negative to positive or positive to negative, right? If it doesn't change signs, then it won't be a point of inflection and it won't be a max or min. Is everybody good with that? Okay, now think about this. If the second derivative is positive, then and the first derivative equals 0, then I'm going to have a minimum. So minimum happens when f double prime is at c is greater than 0 and the first derivative equals 0. And a maximum happens when f double prime of c is less than 0 and the first derivative equals 0. I'll draw like a small little graph of what's happening over here. So let's say your first derivative at c equals 0. So what does that tell you? What kind of tangent line do you have? Horizontal, good. All right. And then if I also tell you that f double prime of c is less than 0, then you would tell me that it's concave down. So if you have a horizontal tangent line and it's concave down, there's only one point that could happen, and it would be at a maximum. Do you understand that? So that's why it's called the second derivative test. You're using the second derivative and the first derivative to prove it. Okay, if your first derivative at c equals 0 and your second derivative at c is greater than 0, you've got a horizontal tangent line and you have a concave up graph. So this has got to be a minimum, right? Okay, important to note, I don't have this anywhere on the packet, so I should probably put it in there next year. But for second derivative test, if you're proving maximums or minimums, you must use for any implicit functions. So you have to use it for if you're given an implicit equation. Are you okay with that? Because think about it this way. If I have an implicit function like x squared plus y squared equals 25, if when I graph that and it goes all the way around like this, right, because that's the equation of a circle, does it follow like a straight number line? No, because I go over this way, but then I also come back around. So it doesn't follow a straight line. So if you want to prove anything is a maximum or a minimum, then you have to prove right here that dy dx equals 0, like the first derivative equals 0, so it's a horizontal tangent line, and you want to prove that the second derivative is less than 0. So then you say, oh, at that point, my first derivative equals 0, but my second derivative is negative, so I know that at that point it's a relative maximum. Does that make sense why you have to do it, the second derivative test for implicit functions? Okay, no number lines for second derivative tests because you can't do a number line for any implicit functions. All right, now we're back to original explicit functions. So let's use the second derivative test to find relative extrema for each function. So here's g of x. Let's find our critical values first. So where g prime of x equals 0, so 4x cubed minus 24x squared. Our critical values are when I set it equal to 0. I'll take a 4x squared out. So x equals 0 and 6. Okay, so those are our critical values. That's where the tangent line is horizontal. Then let's find the second derivative. So the derivative of 4x cubed minus 24x squared is 12x squared minus 48x. Right? And then if you want to, you can simplify, but we're not going to set it equal to 0. So 12x, x minus 4. That's what g double prime equals. Okay. Now, if I plug in 0, then I get 0. So does that tell me at 0 I have a max or a min or anything? No, this tells me nothing. No max or min. And then if I plug in 6, I get a, yeah, it doesn't even matter what it equals. Let's change that to just, this is just greater than 0, right? So then that means it's concave up, right? So if it's concave up and I know my first derivative equals 0, so first derivative equals 0 and it's concave up, then what is 6? Yes, so you can say relative min at and then if you wanted the actual point, you just say 6 comma, and then you can just write it like this: 6 to the 4th minus 8 times 6 cubed minus 5. Don't even need to solve for it. And if it asks you to justify your answer, you would say because f prime at 6 equals 0 and f double prime at 6 is greater than 0. And that would be enough justification. Okay? Easy peasy. Oh, too fast? Anybody need this? Okay. All right. Concavity. This is concave up, like a cup. This is concave down, like a frown. And this is a point of inflection. Concavity, if it's concave up, then if you draw little tangent lines, then are they on top or below? On the outside. They're below the curve, right? So this is important to note, especially when we do linearization. If it's a concave up graph, all tangent lines lie below. So concave up, tan lines are below. Oh man, I can't spell below. And then if it's concave down, then you have all your tangent lines are above. And if the tangent lines lie exactly on the curve, then it's probably a point of inflection. Yeah. Okay, cool. We already know this. If the second derivative is greater than 0, the graph is concave up. If the second derivative is less than 0, the graph is concave down. Increasing, if the first derivative is greater than 0 and the second derivative is less than 0, or no, also greater than 0, then it's increasing and concave up. So the graph looks like that. And then decreasing and concave up would look like this. And then increasing and concave down looks like that. And decreasing and concave down looks like that. Right? And if the second derivative equals 0, it's increasing and you have a point of inflection. So you should be going up with like a point of inflection right there. And then if the second derivative equals 0 and its first derivative is less than 0, then you're decreasing with a point of inflection. So it looks like that. It looks like a, yeah. And then this one is first derivative equals 0 and second derivative equals 0. It could be a point of inflection, but it could not be. Usually that looks like this, but not always. But there's your point of inflection right there. Like an x cubed kind of thing. Okay. Everybody good? Excellent. Okay. Given f of x equals 1/3 x cubed minus x, concave up or down. So we need to find second derivative, right? So first, actually we have to find the first. I'm ahead of myself. So x squared minus 1, right? And then the second derivative would just be 2x. Okay, now what should I do? Solve by setting it equal to 0. Okay, so we've got x equals 0. If I do a number line, then I'll put 0 on it, and I'll put f double prime here so that I know I'm plugging all of these into my second derivative. So if I plug in -1, then this is negative, and if I plug in 1, then this is positive. So what does that say that f is doing? And f on the right side of 0 is concave up. Okay, and so on free response you would have to say concave down from -infinity to 0, concave up from 0 to infinity. And this one doesn't ask you to justify your answer, but if you had to justify your answer, you would say because f double prime of x is less than 0, and you'd say because f double prime of x is greater than 0. Okay? Now, if you wanted to connect it, you could, because right here, if you're concave down, then what is f prime doing? Decreasing, and then on the right side, f prime would be increasing. So if you were to graph f prime, it would be decreasing up till 0, and then increasing from 0 on, and that would be the graph of f prime. And if you graphed f of x from f prime, then you would know that it is f is going to be increasing until, hey, thank you. Andy, this is for you. You be increasing until what? -1, and then decreasing from -1 to 1, so you'd be increasing up until -1, decreasing from -1 to 1, and then increasing again from 1 on. So that would be your original f of x graph. So you can go all the way backwards. No? No, it's not too bad. Okay, am I going too fast, or are you okay with concavity and second derivative? Too fast? Okay, good. Yes?
On a test, do you ever have to actually draw a graph?
I don't think you ever do, actually.
Well, like, I know at least last year we did it. I didn't have to do it.
No, they usually don't have you draw graphs, but they do have you analyze graphs that are given to you. Okay, points of inflection. It's where f double prime of x equals 0 or f double prime does not exist, but I'm missing something here, because just because the second derivative equals 0 does not necessarily mean it's a point of inflection. What does it have to do? Yeah, I actually have to change concavity, right? I can't go concave up 0, concave up to be a point of inflection. So I have to this has to change signs. If it doesn't change signs, then it's not necessarily a point of inflection. Because right here, we're concave up, and then we're concave down, so that's a point of inflection. Here, we're concave down to concave up, that's a point of inflection. And here, we're concave up to concave down, and that's also a point of inflection. But there's times where it could possibly not be. Yes?
What would a point of inflection on the second
Oh, there you go.
I don't know. On the second derivative?
Yeah.
That's something about the fourth derivative.
So the fourth derivative equals 0.
Yeah.
And
S- Fourth derivative is snap. It's where snap equals 0. No, third is jerk. No, fourth is jerk. You're right. Snap. It would be crackle. It's where crackle equals 0.
Is that fourth jerk?
Third is jerk.
No, third's jerk.
Yeah, you're right. Third is jerk. Ah, creepy. You've got me all messed up. Third is jerk. Then fourth is
You always
snap.
remember by the t-shirts these TJ students wear.
Yeah, the third derivative.
Yeah, that's true.
Yeah. You told us.
Yeah, you
I know. Guys, I tell you a lot of things. The thing is, not a lot stays in here, which is why I teach math, because I can rediscover it all. Like, the good thing about math is that if you know, like, the fundamentals, you can, like, reprove everything to yourself to try to figure it out.
Helps when you write your own quote.
That's why I'm terrible at history. I can't remember, like, dates or facts. That's why I don't argue with people about, like, things that have happened, because I probably don't know what happened. My mom, when I was younger, she would, like, take me to go see movies, but then she would, like, quiz me afterwards and be like, who is this character? What did they do? What was the plot? And I'd be like, I don't know. I don't know what's going on. So then I would sneak in a little notepad and I would write down what these people's names were and stuff, so that when she quizzed me, I could, like, review it and, like, tell her later.
Oh my god.
Yes. A little glimpse into the childhood of Miss Moy. It was fun, though. Not really. I mean, like, in a intimidating, terrifying kind of way.
I'm excited for the people who come and watch these notes once we're done with them.
Yeah, exactly.
Have a great time.
Yeah.
Like, who is this kid asking about the point of flex?
Well, that's good. Then they'll be like, oh, my class is really boring compared to this one. Okay. Let's finish. How about you try example 3? We're gonna skip example 5 because it's really hard to see on a calculator. So we're not gonna do example 5, but we'll do example 4 together. But try example 3, find the first derivative and the second derivative, and then do a number line chart to find it concavity and points of inflection. Negative. Did you already finish?
We do 4.
No, we're gonna do 4 together. Okay. Yeah.
They give you like really hard derivatives in the test. The rest of the year you get really easy concepts like extra versus like fractions or something.
Well, you want fractions?
Just ask you if we get easier derivatives as the year goes on.
Why would you get easier derivatives as the year
Why
goes
would
on?
these derivatives when you're getting fractions?
These aren't even hard.
That's
Right, well, we haven't put sine and cosine and e's and natural logs in yet.
That's when it gets really hairy.
I mean, it's fun. It's all about the mentality. If you think it's fun, it'll be fun. What? Yeah, I think it's true. When I smile and I'm not in a happy mood, I get happier. My happiness increases. My first derivative is positive. Is that nerdy? Okay, let's do example 4. If I do, okay, here's example 4. If I graph that y equals x squared minus 3 plus sine 2x minus 1, this is the graph that comes up. Can you find points of inflection from this graph? Not easy, right?
no.
Okay, so let's go back to y equals, and we don't need to look at that graph. Let's go to, yes.
What are the answers to 3?
Oh, I'll put it back up in a second. Okay. Let's go to y4. This is the first derivative, right? Do you still have that in your calculator?
No.
Okay. Don't delete it. Just put it in like y4 or y5 that you'll never use, and then turn it off. And then turn it back on when you want to use it again. You know? Pro tip. What? Yeah, there is calculators for the test.
No, he's asking if they clear it.
It's half and half. Do they clear them? I don't think they do them. I don't think they do clear. Before the test? Well, I'm going to now. Jeez. Freaking me out. Okay. If you were to do the second derivative, because this is the derivative of the derivative, this is what it would look like. But I think if you try it, you can try it in your calculator. Mine will go fast because it's a computer, but I think yours is going to take, oh, also change your window from 0 to 2 pi. I think yours is going to take like a century to do.
And then I don't want to do it.
If you don't have to get assignments, just graph it.
Oh, actually, yes.
Does it take a really long time?
It's not that bad. It's going.
Okay. So maybe you like let it go, try another problem, come back to it. Yes.
When you're writing, like where it's up, down,
Mhm.
I have like what type of bracket?
Open parentheses, because when it equals 0, it's not either concave up or concave down. So at those singular points, it's always open because they don't equal.
I put in parentheses, but it's
Yeah.
and it had brackets.
I got the
Oh, that's
Put
wrong.
brackets. It was wrong.
What?
I got the exact opposite of your graph.
Like the flip of it?
Are you in
Yeah.
radians?
Yeah. Are you in radian mode?
No, I figured out what happened.
Oh, did you put cosine?
No, I made it positive and negative.
Oh, did you make? Oh, you made this negative sign?
Yeah, no, I made the 2x minus 1, so.
Oh, that'll do it. Okay, so how many points of inflection do we have?
4.
4. It changes concavity 1, 2, 3, 4 times.
I don't know how to do it.
Why?
Definitely not.
Because if this is the graph of the second derivative, Eric,
Yeah, I know, but like, how does it work?
That's
on
the
my graph?
graph, the second derivative.
How does?
right there. You said
I don't
Oh,
see how it
second
changes
derivative.
my
Oh,
original
okay.
graph.
I was like,
yeah, you don't.
I see the graphs going-
I think you'd have to zoom in, and if you drew tangent lines at every one of those points, it would change to tangent lines above the curve, below the curve, to above the curve, to below the curve, to above the curve, to below the curve, to above the curve.
Alright.
Yeah, it's a very slight change. All right, you can also tell from the first derivative, so if you didn't want to graph the second derivative, you should be able to find points of inflection from the first derivative. How?
Horizontal.
Yeah, every time you reach a maximum or a minimum on the first derivative, your second derivative should hit 0, right? And change concavity. So 1, 2, 3, 4. You don't have to graph the second derivative. Just make sure you know the connection between all of them. Okay, here you go. All right, so this was 4 times. All right. All right, let's try 6. Let's find our critical numbers. Negative 15x to the 4th plus 15x squared equal to 0. Take out a negative 15x squared. Yeah. You got plus or minus 1 and 0. Okay, find where the second derivative equals 0. I don't know why you need to find where the second derivative equals 0. If you're just using second derivative test, you don't have to find where it equals 0. Let's just find the second derivative. Did you do it already? Negative 60x cubed plus 30x. Sometimes it's easier when you're plugging in to factor it. So that you have it nice and factored. Otherwise the numbers sometimes get really big.
Isn't it 2x squared minus 1?
Oh yeah, because I took out a negative 30.
Yeah. That would have went off the test.
I think it's like the first time something.
Andy's right on today. Not sabotaging me like last class.
It's because he's not taking his
I did. Maybe less than one.
Derivative at 0 is, second derivative at 0 is 0. Second derivative at 1 is positive or negative. And second derivative at negative 1 is
Andy.
oh, Andy, you are on a hot streak for one question. Okay, so sine of the second derivative, if your point is 0, comma, plug it back in the original 0. Our sine is 0. Conclusion, none, right? We don't know what happens there. We could say possible point of inflection, but unless I prove that it changes from positive to negative, then I can't say anything. Then we have 1 comma, what is this? Negative 3 plus 5, 2. And your second derivative is negative, so what is it? Concave down, horizontal tangent line. maximum. Yeah. And then we have -1 comma, and we have +3 -5 -2. Ooh, Andy, back on point. Positive double derivative, and then conclusion, it would be a minimum. Yay. Good. Ooh, this is the graph of f prime. Tell me where f is concave up, concave down, and points of inflection. So points of inflection happen where on the first derivative?
Zeros.
Good. Maxes and mins. So points of inflection, point of inflection. And if it's decreasing on the first derivative, then what is it on the original? So f double prime would be negative, right? And then it's positive here, and it's negative here. So if it's decreasing on the first derivative, then the original is concave down. Good. And if it's increasing on the first derivative, then the original is concave up. And decreasing on the first derivative means that the original is concave down. What? Yeah, everything is so intertwined. You can tell a lot about this. Okay, do you need like a 2-minute break? Keep going?
We have like
At the end, you can leave earlier.
You can't leave earlier. What is this?
Well,
the majesty.
Yeah, John just is like, this is not like a college class. We live and die by the bell.
Then I just go to.
I don't do service hours.
No, because we're going to start in like a
No,
minute.
it's like
This boy, do you need
I
these
just
service
need to
hours?
get a document.
You can do it in a minute. What?
You need these service hours.
The minute service hours.
Like for 1 minute?
No. I feel like do you have anything for me to do after class?
Oh, after today? Or like later this week I will. Okay.
Wait, so it's the second derivative is positive, it's concave up, negative, concave down. Right.
Yeah. And if the
I was trying to get,
second
like,
derivative is
What?
if the second derivative is positive, that means that the first derivative is increasing.
If the second derivative is positive?
It means the first derivative is increasing and that the original
Is
is
that not what the
concave up.
first derivative does? The second
The first derivative
is
tells
positive,
you
the first
whether
derivative
the original is increasing or decreasing.
Oh, okay, I got you,
Yeah,
I got you.
I like to do this chart, like, so here's F prime, and F double.
No, I misheard when you said the first derivative.
Yeah, okay.
I thought you were talking about the original function. I was like, never heard that one.
So if the second derivative is positive, then the first derivative is increasing, and the original is concave up.
Okay.
And if the first derivative is positive or negative, then the original is increasing, decreasing.
All right.
That's the connection.
You said same as you deserve it. Okay, cool.
I didn't.
Okay, I got 2 more problems to do with you
Today?
today, and then you are free to do those 3 things. Okay?
Remind message you with missing away with like 10 pounds.
Who
Andrew
would do what?
like remind text you this boy with like
Oh yeah.
Source for counter.
flashbacks. It took a while.
All right. for curve sketching, what you want to do is you want to put together everything you know from pre-calc
Even nothing?
and calculus all together. Nothing. Guys, Mr. Late and Mr. Matthews would be very upset with you.
That's yeah.
Other side of the continent.
Isn't that
Yeah,
way?
he would be pretty upset. What?
Mr. Moy, do you know what Mr. Matthews is up to?
He's teaching at a
UCLA.
private school in California.
Get rid of stuff like that.
Uh,
I do that too.
It's gonna fall into the freaking ocean. It's gone.
What?
The whole Pacific seaboard. We read an article about it.
The Sharknado.
Well, I mean, like, probably not in a day, so he'll have a day to escape.
global warming.
In the next 50 years, you'll be senile.
10% chance of next.
In 50 years, John's gonna be senile.
Mr. Matthews is gonna be senile.
How old do you think Mr. Matthews is?
Oh, I knew it.
Oh gosh. All right, let's finish this. Oh my gosh, this video.
He told us he grew up in like
Yeah.
Yeah. Yeah. We saw that.
I still have
So, f prime, whatever that is, that's a derivative, right?
Oh, you can watch this. We're recording
But
this.
what's
as
the
well.
double
Second derivative.
second derivative?
Yeah.
So then more
Wait, a
possible.
derivative is the slope of the tangent line to the function
Yes.
at a specific
Yes.
point.
So what's
Yes.
the
So
right
basically,
So what is the second derivative?
It gives you the slope of the tangent line of the first derivative.
Guess what the third
Oh wow!
I think I'm in the wrong class. Sorry.
Wow, you look just like a student.
Thank you very much. Takes 5 years off. Can you need help with that, Mr. Plucker? You got
Yes,
it.
I do. What's the second derivative?
Second derivative? Well, obviously you have the first one, and then you have the second one.
I knew that the derivative is the slope of the tangent line to the function.
Of course.
Okay. Can I draw for a second?
Sure.
All right. So you have a function. Okay. There you go. So, like, pick your point. That's your tangent line, more or less, right?
Yeah.
Okay. So I don't understand how you can have a slope on that.
So the second derivative is the rate that the slope is changing at that point.
As opposed to the rise.
It's like the accelerator.
But how can the slope change when it's only looking at the slope of a tangent at a particular point?
Okay, so you can make a graph for the first derivative with like every single like point on it.
Right.
Then you can take the slope of that new graph.
Think of it like your car. You first have distance, the velocity, and acceleration.
Right.
But the one you just drew doesn't have a second derivative. Because what you're saying is that you can't find the slope of that, right? So it'd be 0. Yeah. Because it's a horizontal line.
Okay.
If you had it like a different graph.
Okay, wait, hold on.
You should come take our test next time.
Yeah, take it for us.
All right.
What is space?
So that's point. That's the
Slope of the
tangent, right? And so
Yeah.
the derivative is that slope right there. So basically, then I'd take another point and I'd find another. And so the second derivative is like all them.
So you know how that's the first line you drew was less steep than the second line,
Yes.
right? So the second derivative finds the change in the slopes, the rate of change of the
So
slopes.
you need basically at least 2 points then, or is it like all? Are you sort of looking at
all points
all
combined.
points
Yeah.
combined?
Let me help you, Mr. Plunkett. See, When you're talking about a slope like this, you just gotta put a little tip like this. And then put a little,
Are you trying something?
and he's down the slope. Which then gives you the second derivative down here.
Okay.
Does that help? So that'll be on the test. Make sure you memorize.
I got it. You
Don't
guys got
draw that on the test, guys.
Make sure you have the guy skiing on the slope, okay?
Do you want my AP scores to stay the way they are?
Gotta help.
Okay, go for it. Let's see what you're doing.
Okay. All right, let's put it all together. So, can I find x-intercepts easily? Does this factor nicely?
Yes. I mean, if you split it into 3 factors,
Let's try. Like, if I split it in 2, then I could pull out an x squared here. And nothing here. So it doesn't come out nicely. Although, you know what? If we really want to go throwback, we could do P over Q
We don't need to do that.
and do some synthetic division. Okay, I won't make you do that.
days are over.
Okay, can you find me other things like a y-intercept?
Yes.
Okay, so 0, -2 is my y-intercept. What's my domain?
Negative infinity.
Okay, so domain and range,
All real numbers.
all real numbers. Cool. So we know we have this 1 point, 0, -2, to start with. All right, now let's find our first derivative. And then what should I do? It's what? Oh, we already have the y-intercept. Okay, find our critical values. Yeah, we'll take out the 3.
So 3 and 1.
Thank you. Andy,
Yeah.
positive or negative?
X equals 3 and 1.
Oh, okay, you already went here. Okay, cool. So if I do a sign chart for that, then I've got f prime and 1 and 3. What's my signs?
Positive before the.
Okay, positive, negative, positive. What does that mean for the f of x graph?
Decreasing, decreasing, decreasing.
Increasing, decreasing, increasing. Cool. Any additional information that tells me? Good. The min and the max. 1 is a max and 3 is a min. Awesome. Okay, let's do our second derivative and see what's up there. 6x minus 12. Set that equal to 0. And then we do a number line for the second derivative. Where do we go? So when I plug in 0, it's negative, and then positive. Cool. Oh, good. So what does that tell me that f is doing?
Concave down and concave.
Concave down and concave up. All right. Since I know that 1 and 3 are my max and my min, let's go ahead and get those y values so that I can at least plot them. So if I plug 1 in here, what am I going to get?
2.
need double verification for Andy. And if I plug 3 in,
That's too many.
negative 38?
We got negative 2.
Isn't it like negative 50?
I'm gonna go with Eric. Negative 2.
34.
Okay, I'm just gonna plug it in.
I got negative 38. Oh,
Well, so there's two.
okay, yeah.
Then-
It's negative 2.
I don't know, it's negative 2.
Yeah, it's negative 2.
Calculate
Okay.
confirmation.
All right, at 1, 2, we've got a point here, and then at 3, negative 2, we have a min here. So we've got a max here and a min here. And then let's go ahead and find our point of inflection. If I plug in 2, zero, right? Yeah, I need double.
Yeah.
0? Okay, thanks. All right, 2, 0. So, we should be increasing up until 1, decreasing from 1 to 3, and then increasing from 3 beyond. And then I should be concave down up till 2, and then concave up from 2 and beyond. So, graph your... So, increasing, concave down, then we're decreasing here, and then decreasing but concave up, and there is your function. Okay, Mr. Plunkett?
What did you just graph? Is that the second derivative?
No, we graphed the original function
Original,
based on information that we found from our first and second derivative. Yes.
How do you calculate the,
The x-intercepts? Or what? Okay. Okay, how's everybody feel? Okay? All right, let's do example 2, super...
That's...
Okay, it's not going to be super fast.
Yeah.
Sorry. Yeah, and I'm going to have to talk to you a little bit about certain simplification things that you'll need, because otherwise it gets really messy if you don't use it. All right, what do we have to do to find our first derivative? Yeah, everybody's favorite. Start with bottom. Bottom times the derivative of the top minus the top times the derivative of the bottom all over bottom squared. Okay, at this point, here's something that you should know how to do. See how this term has a 2x and this term has a 2x? Yeah? Okay, factor the 2x out. And then you have x squared minus 9 minus, and then distribute that negative, x squared minus 1. And then you don't have to do a whole bunch of crazy factoring. And so if we simplify the inside, we get negative 10, and then times 2 would be negative 20x over x squared minus 9 squared. Yeah, it makes it a lot easier. Okay. What should I do? What are my, wait, hold on, critical values first.
3.
x equals 0 and plus or minus 3. Because not only do we want where the second derivative equals 0, but we also want where the second derivative is undefined, right? Because things happen wherever it's undefined. So we have to keep it. All right. Second derivative. I know, deep sigh. Bottom derivative of the top minus top derivative of the bottom. Over bottom squared, right? Nope, to
No,
the,
it's full.
thanks Andy. Hey, save me. Okay, what do these two terms now have in common? Negative 20, so I can pull out a negative 20, anything
X
else?
squared minus 9.
And then 1 x squared minus 9 in each term. So let's take out a negative 20 and 1 x squared minus 9. And then what's left in this one?
X squared minus 9.
Just an x squared minus 9. And what's left in this one?
4x squared.
So it's still minus, right?
Yeah.
4x squared.
That's it.
That's it. There's an x here. Do you see that one? There's an x here, a 2, and a 2, and an x. His son is taking calculus right now.
AB. Hoping to see next year.
So he's learning with him.
I'm not ready for this yet.
Okay. Is that it? Am I good? All over x squared minus 9 to the 4th.
To the third.
Okay, yeah, I'm going to change it. I'm going to change it to the 3rd by canceling out this one and this one down here. So what I have left is negative 20 and then negative
3x minus 9.
3x squared minus 9, yeah. All over x squared minus 9 to the 3rd. Okay. It's not too bad because
Negative 3 coming.
I could. Do you want to? Negative 60. Positive 60. X squared plus 9 or plus 1? 2. 3. I mean, 1 plus 2 equals 3. Okay, cool. Do I have critical values here?
Yeah.
0.
Just at plus or minus 3, right? Because the top won't give me any zeros.
Wait.
Oh.
Because it would be equal to negative 3 and then square root would not give me
Yeah,
anything.
okay.
Okay, now let's test. 0, negative 3, 0, 3. Ooh, negative 4 is positive, positive, right? Negative 2 would be positive, positive. 2 would be negative, positive. And then 4 would be negative, positive. Okay, so we should be increasing, increasing, decreasing, decreasing. And then our second derivative, negative 3 and 3, is negative 4. Positive that positive?
Yeah.
Yeah, it's possible.
0. Positive,
Okay.
negative.
And positive.
Okay. So we are concave up, concave down, concave up. All right, on the original, I forgot to do this at the beginning. Tell me, do I have any x-intercepts?
Maybe.
Yes.
No.
Yes.
No.
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 I.
Because we can't set that equal to 0, right?
Yeah. No. Obviously not.
Do I have a vertical asymptote
Yes.
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 at?
3 plus or minus 2.
Okay, so asymptote here, asymptote here. Any other asymptotes?
Horizontal.
At 1. X, oh, so we have no x-intercepts. Y-intercept? Negative 1/9. Good. That's a weirdo point right there. But there we go. Okay, so I'm increasing basically up till 0, and then I'm decreasing from 0 on. So increasing, and then I'm concave up till -3. So concave up, increasing. Yes.
How do you know horizontal asymptote?
Because the degrees are the same. So leading coefficient over leading coefficient. Okay, and then we're concave down from -3 to 3, and we're increasing then decreasing. So this will look like a parabola. And then we are decreasing from 3 on and concave up. Decreasing, but concave up has to go on this side. And then that's it. Cool, huh?
So data.
So neat.
What would this equation represent in real life?
So there's, what is this, undefined? When you're like 3 years old, you just decided not to do anything. I don't know. Yeah, exactly.
That sounds weird.
How do you know?
Freshman year.
All right, so they cut, Mr. Hood and Mr. Plunkett cut into my time. I'm sorry.
Yeah, I recorded.
But there's,
Really on the board.
now you still have it's 2:34. You have about like 20 minutes left to work on Delta Math quiz corrections or your optional review. Yeah, if you want to turn in quiz corrections right now, you can.
What about the last two?